Today we're going to talk about logarithmic functions and their graphs. In the last lesson we studied exponential equations. The inverse of exponential equations are logarithmic equations. So logarithms are to exponentials what division is to multiplication. All right, so let's look at the definition of a logarithmic function. For x bigger than 0 and a bigger than 0 and a not equal to 1, then y equals the log base a of x if and only if x equals a to the y power. So these two things mean the same thing, they're just written differently. And the beauty is, if I want to solve something like this, oftentimes I can change it into something like this, and it's much, much easier to solve. Okay? So the function given by f of x equals the log base a of x, and that's the way you read it, log base a of x. This is your base, okay? This is your exponent over here, okay? Is called a logarithmic function with base a. All right, and y equals the log base a of x, and x equals a to the y are equivalent equations. All right, now this is a really important statement right here that I want you to keep in mind. Logs are exponents. That's all they are. Logs are exponents. All right, so if you get confused, just say that phrase in your head, logs are exponents, and then go back, and sometimes that'll help you solve the problem. Okay, so how do we do this? So evaluate each logarithm with the indicated value of x. So what we need to do is we need to solve the log base 2 of 32. All right, so here's what I would do. I would rewrite this as y equals log base 2 of 32. And then I can rewrite that. Remember, here's my base. So there's my base. This is an exponent because a log is an exponent. And that equals this number right here. So 2 to the y power equals 32. All right, so 2, 4, 8, 16, 32. Y is 5. Okay, over here, g of x, the log base 3 of x, where x is 1. Okay, so we'll rewrite this as y equals the log base 3 of 1. So my base is 3, my exponent is y, and the answer is going to be 1. And 3 to what power equals 1? Well, any number to the 0 power is 1, and so there we go. Y is 0. All right, over here, the log base 4 of x, where x is 2. So y equals the log base 4 of 2. So 4 to the y power is 2. So y ends up being 1/2. 1/2 is the square root of 4, and that's 2. Or the y power is the square root. Okay. And lastly over here, log base 10 of x, where x is 1/100th. So y is the log base 10 of 1 over 100. Okay, so 10 is my base, y is my power, that's 1/100th. And so y is going to be negative 2. Because remember, a negative power flips it over. So that would be 1 over 10 squared, and 10 squared is 100. So there we solved some logs without a calculator. All right, so this is not going to be so easy. You know, we're going to use a calculator to evaluate f of x equals the log base 10 of x at each value of x. So at this point, you need to get out your handy-dandy TI-84 plus C Silver Edition graphing calculator. And if you look right next to your 7 key, there is a key that says LOG. That's your log base 10. Anytime you see a log and it doesn't have a number right here. It's assumed to be log base 10. Okay, so what we need to do is we need to find the log base 10 of 10. Well, that's one we could actually do in our head pretty simply. We're going to do it on the calculator here. So you're going to push the log key, and remember that's automatically the log base 10, and you're going to put in 10 and close the parenthesis and hit enter, and it's 1. And that makes sense because 10 to the 1 power is 10. Okay, over here, we want the log base 10 of 1/3. Now, this is not one you're going to do in your head. Okay, so I'm going to hit my log key. I'm going to put 1 divided by 3 and then close the parentheses. And I get approximately equal to negative 0.4771. 4 digits is far enough to go. All right, on this one, we want the log base 10 of 2.5. Okay, so log key, 2.5, close the parentheses, hit enter. It's approximately, should use approximate signs, 0.3979. And lastly, I'll let you do this one on your own. So put this on pause, do this, and see what happens, and then pop back on here. Okay, so we're going to do the log base 10 of negative 2. All right, so log key, negative 2, close the parentheses, enter, and I get a big fat non-real answer error. Okay, why is that? Well, because I want this to equal some number, and 10 to the y power is supposed to equal negative 2. And you can't do that, okay? If you look at a log, so if you think about 10 to what power is going to equal a negative number? Well, 10 to a positive power is going to be a bigger number, right? So 10 squared is 100, 10 cubed is 1,000, and so on. 10 to the 0 is 1. 10 to a negative number, so 10 to the negative 1 is a tenth, 10 to the negative 2 is a hundredth, 10 to the negative 3 is a thousandth. This thing is never going to be negative 2. Okay, so yeah, this has no real solution. Anytime you try to take a log of a negative number, it's never going to work. Okay, so some properties of logs. The log base a of 1 is always 0. So it doesn't matter what the base is, it's 0. And the reason for that is, remember if I rewrite this as an exponent, okay, a is my base, this is my exponent, and this is what it equals. So anything, a stands for anything in this case, anything to the 0 power is 1. The log base a of a is 1, all right? So that makes sense because, again, if I rewrite this thing as a to the first power, guess what that equals? A. The log base a of a to the x is x, okay? So if I rewrite this as an exponential, here's my base, here's my exponent, that equals this number right there, and, of course, a to the x equals a to the x. And then finally, if the log base a of x equals the log base a of y, then x has to equal y because, well, I'm doing the same thing to both of them. So it has to be the same number if these two things are equal. Okay. So using properties of logarithms, solve for x. So the log base 2 of x equals the log base 2 of 3. Well, from that last theorem that we just had, this tells me that x must be 3. Okay? Because I can basically, what I can do is just say, hey, I got a log base 2 on both sides. I'm just going to eliminate that. X equals 3. All right, the log base 4 of 4 is x. All right, this is one that I'm going to do by, I'm going to change this to 4 to the x power equals 4, and now it's obvious x is 1. Simplify the log base 5 of 5 to the x. Okay, so I want this to equal y. So 5 to the y equals 5 to the x. So y is x. So my answer is x. All right, this is an interesting thing. 7 to the log base 7 of 14. Okay, so I've got an exponent here that's a log. Now, logs and exponents are like multiplication division. So this would almost be like saying take 7 times 2 and then divide it by 2. Well, what do you end up with? Well, the times 2 and the divided by 2 cancel out. And that's exactly what happens here. 7 to the log base 7, that cancels out. I'm left with 14. Okay. So let's sketch a graph of 2 to the x and log base 2 of x. So 2 to the x, that's pretty simple. We've done that before. 2 to the 0 is 1. 2 to the first is 2. 2 to the second is 4. 2 to the third is 8. 2 to the negative 1 is 1/2. 2 to the negative 2 is 1/4, 1/8, and so on. So this looks like this. That's 2 to the x power. Now, what does a log look like? Well, here's the thing. Let's say this is log base 2 of x equals y. We can rewrite this as 2 to the y equals x. Okay? So if I want 2 to the first power would be 2, right? So my x is going to be 2 and my y is going to be 1. And 2 to the second power is 4. So my x is going to be 4 and my y is going to be 2. 2 to the third power is 8, so my x is 8 and my y is 3. 2 to the 0 is 1, so my x is 1 and my y is 0. And I know that 2 to the negative 1 is 1/2. So 1/2 would be negative 1. And this is going to go like this. So this graph is going to go look like that. Now, when I said that logs and exponents are inverses of each other, if you remember, inverses are if you graph inverses, they are a reflection of each other in the line y equals x. And so if I draw the line y equals x, there's the line y equals x right there. You can see they're a mirror image of each other in that graph. So the other thing is, if you need to graph a log, and logs, are a little bit harder to understand in your head than exponents are. You could always graph the exponent, okay, and then just switch the x and y's. So, instead of 0, 1, you're going to graph 1, 0. Instead of 1, 2, you're going to graph 2, 1. Instead of 2, 4, you're going to graph 4, 2. And that will give you the inverse of the graph. And so it's easy to graph that way. All right, sketch the graph of f of x as the log base 10 by hand. Okay, so you know, for me, it's always easier to imagine the exponents. So 10 to the first would be 10, and 10 to the second would be 100. Oh, that's already off my graph. Okay, so 10 to the 0 would be 1, and 10 to the negative 1 would be 1/10, and 10 to the negative 2 would be 1/100th. Okay, so just switch. Normally, this is your x and this is your y. Make these your x's and make these your y's here. So 10/1 is going to be right here. 102, that's off my graph. 10 is going to be right here. One-tenth negative 1 is going to be like right there. This is always going to have a vertical asymptote right here on the x-axis. It's always going to go through the point 1, 0. And it's always going to go through the point, if I have a log base A of x equals y. So the point 1, 0 is always going to be on the graph. The point A1 is always going to be on the graph, and the point 1 over A, negative 1 is always going to be on the graph. Okay, so all the logs, they pretty much look the same. They all have vertical asymptote right here, unless I move it by putting something in here like -1 inside the equation. They're always going to go through this point unless I do something like put a +1 out here outside the equation. And the only difference is going to be the bigger this A is, the sharper this turn is going to be right here. Okay? So, library of parent functions, f of x equals a log base a of x. Okay, so the domain. So I know it's going to look something like this. It's going to go through that point, and it's going to depend on whatever a is. So if I just put a here, then it's going to go through a1. And it's always going to look like this. Okay. And this gets as big as you want. There's no horizontal asymptote here. This gets as big as you want. It just takes a long time to get there. So what's the domain on this? Well, the domain is going to be all the real numbers where x is greater than 0. It cannot be 0 and it cannot be negative. What's the range? Well, the range is going to be all the y's. It's going to be all real numbers because it's going to have all the negative numbers down here. It's going to have 0 right here. And like I said, this will get as big as you want. It just takes a long time to get big. Okay? Intercepts. All right, this has no y-intercept ever, unless I move the equation over somehow. But it does have an x-intercept at 1, 0. This is definitely an increasing function. You can see this thing's getting bigger and bigger and bigger. And it's continuous. I can draw the whole thing without picking up my pencil. Okay, start right here. Draw the curve. Is there any more to this? Nope, that's it. All right, so let's move on. The natural log. Okay, so the natural log is a special logarithm. I suppose you could write it like this. It's the log base e of x. Okay, we don't write it that way though. We write it as natural log, and this is actually log natural. It's French. Okay, so if you look between your 7 and your 4 key, there's your ln key. That's your natural log key. All right, so y is the natural log of e if and only if x is e to the y power. And you'll notice that e to the x power is right above in the blue key. It's the same key, it's just you got to push your second key first. And 10 to the x power is the same key as your log base 10. You just have to push the blue key first. So f of x is the log base e of x, which is the natural log of x. And it works exactly the same way as this one does, e to the x. Goes back there further than I thought it was. Yeah, it's the same as this. Works the same way, except it's the base is e here. Okay. We get everything here? Yeah, we did. Okay. So, use a calculator to evaluate this function. So, I tell you what. I'll do this first one. Find the natural log of 2. All right, so you get out your calculator here, and you just push your ln key, and then you push your ln key, and then you push 2, and you hit enter, and it comes out to be about 0.6931. Now I'm going to let you put this on pause. I'm going to let you figure out these other ones, and then you can jump back on here in a minute and compare your answers to what I get. So go ahead and pause your video right now. Okay, so the natural log of 0.3 is approximately, so I push my natural log key, 0.3, and I get about negative 1.2010, 40, if I round it. Okay, the natural log of negative 1. So I hope that you guessed ahead of time, hey, I can't take the natural log or any log of a negative number. There's no real solution to this. Can I do this? That's kind of a weird deal. Okay, so natural log of 1 plus the square root of 2, and I need to make sure I close my parentheses, and that comes out to be approximately 0.8814. All right, so there we go. Hope you got all 4 of those, or all 3 of those right. So properties of natural logarithms. The natural log of 1 is 0 because e to the first power is 1. If you get confused by stuff like this, you could always rewrite it like this, and then you can rewrite it as, oh, and that makes sense. Okay. The natural log of e is 1. That's because these two things are inverses and they cancel each other out. The natural log of e to the x equals x because e, okay, if I take this and I rewrite it, log base e of e to the x would equal x, then I would have e to the x would equal this number, which is e to the x. Okay, so if you ever want to get rid of a natural log, just take the whole thing to e, and that cancels that thing out. Okay, and the natural log of x equals the natural log of y, then x has to equal y. That's because you're doing the same thing to both sides, and so you can just ignore it. Use properties of natural logarithms to rewrite each expression. Okay, natural log of 1 over e. Okay, you might be able to do this in your head. You might want to say, oh, what's this going to be? Oh, e to the y equals 1 over e, which is another way to say e to the y is e to the negative 1, and so y is negative 1. All right, this one right here, e to the natural log of 5, that just goes away, that's 5. 4 times the natural log of 1. Okay, so the natural log of 1 is 0. Okay, so this is just 4 times 0, which is 0. And finally, 2 times the natural log of e. Well, 2 times the natural log of e is just 1, so this is 2 times 1, which is 2. Find the domain of each function. Okay, so we did some shifting here. So if you remember, if you subtract something inside a function like we're doing here, this moves the function to the right. So if I was to graph this, this thing would look, it would have, instead of having an asymptote at 0, it would have an asymptote at 2. And instead of going through the point 1, 0, it would go through the point 3, 0. So this graph would look like this. Okay, so what would the domain be? Well, the domain would be all the real numbers where x was greater than 2. And it makes sense if you put 2 in here, I get natural log of 0, which I can't do. But I can do anything that's natural log of a positive number, so anything bigger than 2 is going to work. Okay, natural log of 2 minus x. All right, this is one that people screw up all the time. So, 2 minus x, what does that transformation do? Let's see. That's going to move this is going to move it 2 to the left because it's a plus 2, but it's going to flip it upside down. So it's going to move this thing like this, and the graph is going to look like that. So, wait. If I put in, yeah, I can put in 1. Hang on, I got to think about this for a second. So, let's see, this has to be positive. So 2, no, this is wrong. This graph is wrong. Okay, so I can't put in anything bigger than 2 because if I do, this is the natural log of a negative number. I can't put in 2 because if I put in 2, then I get natural log of 0, which I can't do. So this thing is going to have an asymptote at 2. I can put in all the negative numbers that I want. So this thing is either going to go like this or it's going to go like this. I've got to figure out which one. So let's see. If I put in 1, I get the natural log of 2 minus 1 would be the natural log of 1, which would be 0. It's going to cross right there. I just got to do 1 in between here. So if I did the natural log of, if x was 1.5, that'd be the natural log of 0.5, which is going to go down like, it's going to be a negative number, so this thing's going to look like this. Okay, so my domain then is going to be all the x's where x is less than 2. All right, let's look at the third one, natural log of x squared. Okay, so I can't put in 0 because 0, the natural log of 0 I can't do, right? If I put in any positive number, I can do that. If I put in a negative number and I square it, well, that's going to be a positive number, so that should be okay. So the domain of this is going to be all the x's where x is not equal to 0. That's the only one I can't put in. All right, students participating in a psychology experiment attended several lectures on a subject and were given an exam. Every month for a year after the exam, the students were retested to see how much of the material they remembered. The average scores for the group are given by the human memory model. F of t equals 75 minus 6 times the natural log of t plus 1, where 0 is less than or equal to t is less than or equal to 12. So where t is the time in months. The graph of f is shown below. So here's your graph of what they remembered. What is the average score on the original exam when t is 0? Okay, well that's easy. I just plug in 0 here and I get f of 0 is 75 minus 6 times the natural, wow, that's horrible. The natural log of 0 plus 1. Well, the natural log of 1 is 0, and that's 6 times 0 is 0, so that this ends up being 75. So the average score was 75. What is the average score at the end of 2 months? Okay, so I plug in 2. So this ends up being 75 minus 6 times the natural log of 3, right? Because 2 plus 1 is 3. So at this point, I'd get out my handy-dandy TI-84 plus C silver edition graphing calculator, and I'd go 75 minus 6 times the natural log of 3, close the parentheses, hit enter, and it comes out to be 68.4. And that makes sense if you think about it. I mean, people forget stuff after a certain time if they don't use it, right? Most things that you learn are use it or lose it things. If you don't do math for a long period of time, you forget the math. You have to go back and reteach yourself. If you learn a language and you don't use that language, you forget the language. Okay, what is the average score at the end of 6 months? Okay, so f of 6 would be 75 minus 6. Natural log of 6 plus 1 would be 7. So again, I do the same thing. 75 minus 6, natural log of 7, 63.32. And you never really stop forgetting stuff, but over time it kind of flattens out. It takes a long time there's a certain amount of material that you'll keep remembering. Okay, so here's my assignment. A couple of nice math memes on here for you. These are the problems that I would like you to do. And I forgot to attach them to this, so I will definitely attach them to the back of this. And I will also post them on Google Classroom. And so the notes will be perfect for you. So I will see you next time.